Now let's look at another example. In this case, we'll look at something a bit easier. We'll have 101 base 2. So there's no fractional part this time, just a whole number part. So as usual, we'll number the positions 0, 1, and 2. And so this is equal to 1 times 2 to the second power plus 0 times 2 to the first power plus 1 times 2 to the 0th power. And 2 squared is 4. 2 to the first power is 2, but 0 times 2 is 0. And 2 to the 0th power is 1, and 1 times 1 is 1. So we have 4 plus 0 plus 1, which is equal to 5 in base 10. So the binary number 101 base 2 is equal to 5 base 10. Now let's work on one final example of converting binary to decimal, and I hope that you'll try this one yourself first. I want to challenge you with this. We have the binary number 1010.101 base 2. You try to find the decimal equivalent of that. So I hope that you'll stop the video for a moment, try to work this yourselves, and then we'll come back and do it all together. Okay, proceeding in the normal fashion, we'll start numbering the positions 0, 1, 2, and 3 for the whole number digits, and -1, -2, -3 for the digits representing the fractional part. So we have 1 times 2 cubed, 0 times 2 squared, 1 times 2 to the first power, 0 times 2 to the 0th power. We have these four terms here. And then 1, this 1 here, 1 times 2 to the -1, 0 times 2 to the -2, 1 times 2 to the -3. And you see that written down here. Now 2 cubed is 8, and 1 times 8 is 8. 2 squared is 4, but 0 times 4 is 0. 2 to the first power is 2, and 1 times 2 is 2. 2 to the 0th power is 1, but 0 times 1 is 0. 2 to the -1 is 0.5. 1 times 0.5 is 0.5. 2 to the -2 is 0.25, but 0 times that is 0. And finally, 2 to the -3 is 0.125, and 1 times that is 0.125. And if we add all of these numbers up, we get 10.625. So we conclude that this binary number 1010.101 base 2 is equal to the decimal number 10.625 base 10. So that concludes our discussion of converting binary numbers to decimal numbers, and now we want to go the other way around, learn how to convert a decimal number to a binary number. So we'll start with something that we have just calculated, but in the opposite direction. Let's suppose that somebody asks us what 10.625 base 10 is equal to when we go to binary. Now, of course, since we just did this problem, we know the answer is 1010.101 base 2. We know that, but let's see how we could arrive at this answer if we didn't know it already. Well, the way that we're going to do this is called an iterative technique, and you might say iterative technique for converting from base 10 to base 2. Now the way this iterative technique works is the following. We write down the whole number part of the number over here to the left. So we have 10.625. The whole number part is 10. Write that down on the left and write down 0.625 over on the right. Now, for the whole number part, we repeatedly divide by 2. So 10 divided by 2 gives us 5 with a remainder of 0. And notice that I've put R here at the top of a column, and that's going to be my remainder column. And so since when I divide 10 by 2, I get 5 with a remainder of 0, I'll put my first entry in the remainder column will be 0. Now when I divide 5 by 2, I get 2 and a remainder of 1. So this time I put 1 in the remainder column. Now when I divide this 2 by 2, I get 1 with a remainder of 0. And finally, when I divide 1 by 2, 2 won't go into 1 at all, so I get 0 with a remainder of 1. Now, this procedure stops when you get a 0 here in this column. So since we've got a 0 here in this column on the left, we stop. And we now look at our remainder column from the bottom to the top. And we have 1, 0, 1, 0. What this tells us is that when we write this number in binary, the whole number part will be 1, 0, 1, 0, as we can see down here. Now, how do we get the fractional part? Well, over here we have 0.625, and instead of repeatedly dividing by 2, as we did with the whole number part, now we will multiply by 2. So if we take 0.625 and multiply by 2, we get 1.25. The whole number part I'll split off over here is 1, and then we also have 0.25. Now the 1 I'm just going to keep to the side, but the 0.25 I'll carry down to the next line. 0.25 times 2 would be 0.5. So I'll write down the whole number part 0, and then the 0.5 here. And then one last step, if I take this 0.5 down here and have 0.5, and again multiply by 2, this time I'll get 1.0, so the whole number part is 1, the fractional part is 0, and when the fractional part is 0 here, that tells you to stop, and so we have here in this column 1, 0, 1. This column we read from top to bottom, 1, 0, 1, and there you see 1, 0, 1, and here is our final answer, 1010.101. And in fact, if we scroll above, that is exactly what we had before. So this is indeed the binary equivalent of 10.625 base 10. That's, of course, a new concept. Maybe it seems a little bit tricky, and so let's look at another example. Let's take, for instance, maybe something like 63.75. So we now want to convert this number, 63.75 base 10, to a binary number. Well, once again, we'll write the whole number part on the left, 63, and the fractional part over here to the right, 0.75. Again, we want to use the iterative technique, so we will repeatedly divide the whole number part by 2. And I'm going to go ahead and put down an R for the remainder column. So if we divide 63 by 2, we will get 31 with a remainder of 1. If we divide 31 by 2, we will get 15 with a remainder of 1. If we divide 15 by 2, we will get 7 with a remainder of 1. If we divide 7 by 2, we will get 3 with a remainder of 1. If we divide 3 by 2, we will get 1 with a remainder of 1. And finally, if we divide 1 by 2, we get 0 with a remainder of 1. And if we read these numbers from bottom to top, we have 1, 2, 3, 4, 5, 6 ones. So the whole number part will be 1, 1, 1, 1, 1, 1. Now let's look at the fractional part. Now remember here, we will repeatedly multiply by 2. Well, 0.75 times 2 is 1.5. So we write the fractional part here and the whole number part here, 0.5 plus 1. And we'll take the fractional part to the next line. 0.5 times 2 is what? That's 1.0, so the fractional part is 0, and the whole number part is 1. And remember, when the fractional part here is 0, that tells us to stop. And now we read these numbers from top to bottom, and it's 1, 1, so here is our answer. 63.75 base 10, this number here in base 10, when we convert it to binary, we get 111111.11 base 2. This iterative technique can be used not just for converting from decimal to binary, but from decimal to other number systems as well. For instance, suppose that we wanted to convert, let's say, the number 15 base 10 into a base 3 number. Well, we could proceed with the iterative technique here as well. Now, in this case, there's no fractional part, so all we have to do is write down the whole number part and then have a R column. And we need now to repeatedly divide by 3 rather than by 2. So, for instance, if we divide 15 by 3, we would get 5 with a remainder of 0. 5 divided by 3 would be 1 with a remainder of 2. And then 1 divided by 3 would be 0 with a remainder of 1. And now, since we have a 0 here in the left column, the procedure is terminated, and we look from bottom up, and we would conclude that the answer is 120 base 3. So 15 base 10 is equal to 120 base 3. And if we want to check that, we can use the same procedure we used earlier for converting from binary to decimal, but with a little modification now, since we're in base 3 rather than base 2. So the way we would do that is we would say, well, 120 base 3, we number the positions 0, 1, 2, and therefore 120 base 3 is equal to 1 times 3 squared plus 2 times 3 to the first power plus 0 times 3 to the 0th power. Well, 3 squared is 9, and 1 times 9 is 9. 3 to the first power is 3, and 2 times 3 is 6. 3 to the 0th power is 1, and 0 times 1 is 0. And then finally, 9 plus 6 is 15, and indeed, this agrees with what we have over here on the left. So there's an example of converting decimal number 15 base 10 to a ternary number or base 3 number 120, and then going back again to check it. So we have these two techniques for converting from one number system to another. Now, in some instances, there is an easier way to do things, but this other technique only applies in special circumstances. So let's see what that would be. Let's suppose that we had the number 1, 0, 1, 0, 1, 1, 0, base 2. And we wanted to know what this is in base 8. Well, since 8 is 2 to the third power, this technique will only work if one base is equal to the other base to some power. But in this case, that is the situation. 8 is equal to 2 to the third power, and therefore the technique would be as follows. We start here at the point, and since we have that 8 is 2 to the third power, we will group the numbers in groups of 3 as follows. So the first group of 3, as you can see here, is 1, 1, 0. The second group is 0, 1, 0. Now the last group, as we're going from right to left, we just have a 1, so we could add 2 zeros to that and make that a 1. Now, how do we finish this up? Well, 0, 0, 1 is 1. 0, 1, 0 in base 2 is the same as 2. And 1, 1, 0 is 6. And therefore, here is our answer. We have that 1, 0, 1, 0, 1, 1, 0, base 2, believe it or not, is equal to 1, 2, 6, base 8. And again, the way that we got that was just by observing that 8 is equal to 2 to the third power, and then we took the digits in the binary number in groups of 3 and converted each group separately to the appropriate number in base 8. Now, you're probably skeptical about this. You might not believe that it gives us the right answer, but let's check and see. Well, we can number our positions in each of these numbers. So the number on the left is equal to 1 times 2 to the 6th power plus 0 times 2 to the 5th power plus 1 times 2 to the 4th power plus 0 times 2 cubed plus 1 times 2 squared plus 1 times 2 to the 1st power plus 0 times 2 to the 0th power. And on the other hand, this number on the right is equal to 1 times 8 squared plus 2 times 8 to the 1st power plus 6 times 8 to the 0 power. Now let's check both of these numbers and see if they are equal to each other. Well, 8 squared is 64. So this is 1 times 64, which is 64. 8 to the 1st power is 8, and 2 times 8 is 16. And finally, 8 to the 0th power is 1, and 6 times 1 is 6. So the number on the right is 86 in base 10. Now let's check the number on the left. 1 times 2 to the 6th, of course, is 64. 0 times anything is 0. 2 to the 4th is 16, so 1 times 16 is 16. 0. 2 squared is 4. 2 to the 1st power is 2. 0 times anything is 0. And if you add up all those numbers, sure enough, you get 86 base 10. So indeed, this technique that we have shown here for converting from base 2, which is called binary, to base 8, which is called octal, this technique does work, but it only works, again, this technique will only work when one base is a power of the other base. One thing you may have noticed is that when we're working in a certain base, all of the digits that we use will be less than that base. Let me explain what I mean. For instance, when we're working in base 10, we might see a number like this, for instance. Or we might see, we'll say this is base 10, we might see a number like this. But you notice that each one of those digits that we use is less than 10. What I mean, to be certain this is clear, 6 is certainly less than 10, 9 is less than 10, 8 is less than 10, 7 is less than 10, 1 is less than 10, 2 is less than 10, 5, 3, 9, 1, and 2 are all less than 10. If we want to represent the number 10, of course, we take 2 digits to do it. We write a 1 and a 0. Now, similarly, if we're writing in base 2, we would have something like this. Or we might have something like that. Again, all of the digits in this case are less than 2. And if we want to write the number 2 itself, we would again write 1, 0. So in any numbers, whenever we're writing in some base, our digits will go all the way up to that minus 1. So in other words, when we're writing in 10, the largest digit that we have is 9. When we're writing in base 2, the largest digit we have is 1. You remember when we had numbers in base 8, we could have something like this, for instance, 167 base 8, or perhaps 5, 2, 3, 7 base 8. We have all the numbers up to 8, but not including 8. But that raises an interesting question. What about when we have base 16? Now, the reason that this is sort of interesting is that if we're going to have digits for every number up to the base minus 1, then that means we must have digits for every number up to 15. However, we don't know of a single digit that represents 15. I mean, in other words, if we're writing a base 10, we would need to use 2 digits to represent 15. We would need a 1 and a 5. But when we're writing in hexadecimal or base 16, we don't want to write 1 and a 5, because if we wrote, for instance, 1 and a 5, base 16, well, that's not going to be 15 in base 10, right? In fact, it would be equal to 1 times 16 to the first power plus 5 times 16 to the 0th power. So this would be 16 plus 5, and it would be equal to 21 in base 10. So we're asking the following question. If we want to write 15 in base 10, 15 base 10, or our regular old 15, if we want to write that in hexadecimal, how do we do it? And there's no way to figure this out. You have to simply know the answer. And so let me give you the answer. If we want to write base 16 numbers, well, let me back up and say this situation arises for only a few base 16 numbers, and let's see how it goes. So if we're looking at base 10 and base 16, and we're looking at the numbers, 0 in base 10 is written as 0 in base 16. 1 in base 10 is the same as 1 in base 16. Same is true for 2, 3, 4, 5, 6, 7, 8, and 9. They are the same in decimal and in base 16, which is called hexadecimal. But what about 10 in base 10? Now we don't want to write 1 0 in base 16 because, as we know, that would be equal to 1 times 16 to the first power plus 0 times 16 to the 0th power, and that would be equal to 16 in base 10. But we want a number we want to find a one-digit expression in base 16 that will equal 10 in base 10. And what people have chosen to be that one-digit representation is A. And likewise, for 11 we have B, for 12 we have C, for 13 we have D, for 14 we have E, and for 15 we have F. And finally, when we get to 16, then we have 1 0. For 17 base 10, that's equal to 1 1 base 16, etc. So to make sure that this concept is clear to you, let's suppose that we had the hexadecimal number D12F base 16, and we wanted to know what that is equal to in base 10. Well, we can number our positions, and so this is equal to D times 16 to the third power plus 1 times 16 squared plus 2 times 16 to the first power plus F times 16 to the 0th power. Now D is equal to 13, and sorry, I had to go get a calculator. We'll find out what 16 cubed is now. Okay, 16 cubed is 4,096. 16 squared is 256. 2 times 16 would be 32. And then F is equal to 15. And 16 to the 0th power is 1. So we have 15 times 1. 13 times 4096 is 53248, and then 1 times 256 is 256, 32, and 15, and so we finally get 53,551 base 10. So again, to summarize that, D12F16, the hexadecimal number D12F16 is equal to 53551 base 10. Now, just to well, we could check this. This actually is a little, since this number is so big, it would be a little tedious to check this. So let me give you a somewhat easier example, and I'll show you an easy way to check it. So let's look at something a little easier. Let's say maybe 3d2 base 16 is equal to what in base 10? I hope that you'll stop the video for a moment and try this yourself, and then we'll look at it together. Okay, so let's see how we would convert this to base 10, and then we'll see how we can check our work. Okay, well, we numbered the positions as usual, 0, 1, and 2. So the number here on the left is 3 times 16 squared plus d times 16 to the first power plus 2 times 16 to the 0th power. Well, as we said before, 16 squared is 256, and so we have 3 times 256 plus d, if we look above, d is equal to 13, so that's 13 times 16 plus 2 times 16 to the 0th power is 1, so 2 times 1, and this will give us 768 plus 208 plus 2, and we get 978. So we are concluding that 3d2 base 16 is equal to 978 base 10. Now, you might be wondering about an easy way to check this. And let me show you what it would be. Or I'll show you one easy way to check it. And our plan will be this. We will convert 978 base 10 first to binary, and then to hexadecimal. And you might be wondering why I'm taking this roundabout way of doing it. Well, the reason I'm first going to go to binary is we've already learned how to do that. We've learned the iterative technique for converting decimal to binary. Now, of course, we could use that same technique. Remember, we said that the iterative technique doesn't have to have decimal and binary. It could be used for other bases as well. So we could use the iterative technique for going directly from base 10 to base 16. But I want to show you, let's have one more review on using the iterative technique to go from decimal to binary. That'll be useful because we'll review something we've already done. And then going from binary to hexadecimal, we'll use that special technique that we used before to go from binary to octal. In other words, since 2 and 16, since 16 is a power of 2, we'll be able to use the same kind of technique we did earlier to go from binary to hexadecimal that we did earlier to go from binary to octal. So let's see how this goes. So first we're going to go from 978 base 10 to binary. Okay? Well, there's no fractional part, so there's just a whole number part. 9, 7, 8. And we'll have a remainder column. And let's see how this goes. Well, if we divide 978 by 2, we get 489 with a remainder of 0. If we divide 489 by 2, we'll get 244 with a remainder of 1. If we divide 244 by 2, we'll get 122 with a remainder of 0. 122 divided by 2 will be 61, again with a remainder of 0. 61 divided by 2 will be 30 with a remainder of 1. 30 divided by 2 will give 15, remainder of 0. 15 divided by 2 will be 7 with a remainder of 1. 7 divided by 2 will be 3 with a remainder of 1. 3 divided by 2 will be 1 with a remainder of 1. And finally, 1 divided by 2 will be 0 with a remainder of 1. And remember, when we get a 0 there, that tells us that the iterative technique, at least for the whole number part, has finished. And remember that we will read, when we're looking at the whole number part, we read from bottom to top. When we're looking at the fractional part, we read from top to bottom. So since this is the whole number part, we will read from bottom to top. And we conclude that 978 base 10 is equal to 1, 1, 1, 1. We have 4 ones, and then a 0 and a 1, and then 2 zeros and a 1 and a 0. 2 zeros, a 1, and a 0. So 978 base 10 is equal to 1, 1, 1, 1, 0, 1, 0, 0, 1, 0 base 2. That is the first part of what we wanted to do. We have converted 978 base 10, that's a decimal number, we have converted it to binary. Now the conversion from binary to hexadecimal is very simple, because 16 is 2 to the 4th power, and therefore we will group these numbers into groups of 4 digits. We have 4 digits there, 4 digits here, and if we put 2 zeros in front, then we can have 4 digits there. And now we will write down the appropriate numbers for that. 1, 1 in binary, or excuse me, 0, 0, 1, 1 in binary, that first number, 0, 0, 1, 1 is 2 and 1, or 3. The second number, 1, 1, 0, 1, well, let's think about that. That's 8 and 4 is 12, and 1, 12 and 1 is 13. But 13 in hexadecimal is D. So we have D for that part. And then finally 0, 0, 1, 0, that's equal to 2. So we have 3D2 base 16, and sure enough, as you can see up here, that is the original number that we started with. So 3D2 base 16, sure enough, is equal to 978 in base 10. And we've shown that in 2 different ways. So this gives you a good bit of practice in converting from one number system to another. And now we're ready to discuss the first 2 problems. In fact, let's just say one problem this time. One problem on your quiz. Excuse me, your first test. I should say test. Okay. So the problem will be the following. Problem 1 for test 1. We want to, actually, I guess maybe there will be 2 problems. So write one, 2, 3.17 base 10 in binary. I see that this is a problem right away because you haven't learned quite enough to do that. So let me modify this problem. Let's stop for just a moment, and then we will resume. Now let's try that again. I'm ready now to give you two problems for test number 1, and then in our first formal lecture, or excuse me, in our first real meeting, I'll give you probably another problem to do. But the first two problems are these. So for the first problem on test number 1, what I'm interested in is having you convert the decimal number 13.25 to a binary number. And I'll give you 4 choices here. Is the answer 1010.01 base 2, 1100.01 base 2, 1101.11 base 2, or 1101.01 base 2. You need to pick one of those and make a record of it so that you can record it online at the appropriate time. Now for problem 1.2, I want you to tell me 77, the decimal number 77 base 10 is equal to what in hexadecimal. And again, I'll give you 4 choices. Is the correct answer 3F base 16, or 4D base 16, or 2-1 base 16, or 3-7 base 16? So once again now, you should work these 2 problems and make a record of your answers, and as soon as the next class period begins, you'll have the opportunity to record your answers online, and you will be shown in class how to do this. So good luck, and I'll talk to you soon.